All right, here's an example problem with reflecting waves. Small amplitude water waves in shallow water, such that the wavelength is much longer than the depth of the water, travel at a velocity of v is equal to the square root of gh, where g is the acceleration due to gravity and h is the depth of the water. If a wave is traveling in water with a depth of 10 centimeters, and it suddenly encounters a sandbar which reduced the water depth to 5 centimeters, what fraction of the power in the wave will be transmitted into the shallower water? Assume that the wave hits the sandbar at normal incidence. All right, so what does normal incidence mean? It means that the waves, are like this, right? If I draw lines along the crests, they go that way, and the sandbar is in the same direction. So I can kind of treat this as a one-dimensional problem. It's not like my waves are coming in and reflecting off of the sandbar at an angle. Okay, so I can use the stuff we've already used in this chapter because we can treat this kind of like a one-dimensional wave. All right, what we're given, we know that the velocity depends on gravity and the height of the depth of the water. We're given the depth with our incident wave, and we're given the depth of the water in the transmitted side, and we want to find out how much what fraction of the power is transmitted into the shallower water, into the water above the sandbar. Well, we have these equations that were derived in Physics for Fanatics. All right, now we want to find the transmitted wave, right? But I'm going to give you a little hint here. What we want is the power, and I have not given you an equation for the power in a water wave. What does it depend on? Well, the point is, it may depend on how the wave number changes. It may depend on numerous things. It may depend on the depth of water. I don't know, whatever, right? But the point is, whatever it depends on, everything on the reflected side will be the same. The wave number will be the same, the depth will be the same, the velocity of the wave will be the same, except for the amplitude. The transmitted side, there may be things that happen that I don't know how to deal with, right? So what I'm going to do is, instead of finding the transmitted amplitude, I'm going to find the reflected amplitude, find the power of the reflected wave, and whatever doesn't get reflected must be transmitted, right? So in general, power is proportional to amplitude squared. Now it depends on other things, but all those things will be the same on the reflected side. Hello, Kat. You gonna come join us? All right. So if I can find the amplitude of the reflected wave, then the power reflected divided by the incident power is just going to be the amplitude of my reflected wave divided by the amplitude of my incident wave squared. All right? And then the power transmitted, right? The power transmitted, well, the fraction of the power transmitted is just going to be 1 minus the fraction of the power that was reflected. All right? So let's find the reflected amplitude. To find the reflected amplitude, I need to be able to evaluate this, right? So A reflected is equal to this. I didn't tell you what the wave number of the wave was, but I did tell you how the velocity of the wave changed, right? I told you that the velocity is the square root of gh, and I told you that we know h incident and we know h transmitted, right? So remember that velocity, our wave travels one wavelength per period, which is equal to one wavelength times the frequency. The frequency doesn't change when we pass the sandbar, right? The frequency always stays the same. So if I take the ratio of the velocity on the incident side to the velocity on the transmitted side, it will be the wavelength on the incident side divided by the wavelength on the transmitted side, right? So if I do like v transmitted over v incident, according to this equation, since f doesn't change, that will just be lambda transmitted over lambda incident, all right? But because wave number is 2 pi over the wavelength, the ratio of the wavelengths is just going to be the inverse ratio of the wave numbers, ki over k transmitted. All right, so if I come up here and look at this equation right here, if I divide top and bottom by k incident, I can write this as ai 1. Well, let's divide by k transmitted. All right, so this is going to be k incident divided by k transmitted minus 1 divided by k incident divided by k transmitted plus 1. So I just divided top and bottom by k transmitted, and then I look at this equation right here, and I know, K incident over K transmitted is just V transmitted over V incident. So this is going to be V transmitted over V incident minus 1 over V transmitted over V incident plus 1. Okay, so there's my amplitude. My amplitude then, A reflected, is just V transmitted over V incident minus 1 over V transmitted over V incident plus 1, right? And then we said, oh, but that V transmitted over V incident, that's just the same as, right, the velocity goes as the square root of h, so that's just the square root of h transmitted over h incident, which are given, divided by the square root of h transmitted over h incident plus 1. All right, so I plug that in, and I can get the amplitude of my reflected beam, right? And in fact, this ratio is just, we went from 10 centimeters incident to 5 centimeters transmitted. So this is going to be the square root of 1/2 minus 1 divided by the square root of 1/2 plus 1, right? Because the transmitted is lower depth, is half the depth of the incident side. Okay, so then I get this thing right here. What do I do with it? We said that the power can depend on lots of things, but on the reflected side, everything is the same as the incident side. So the power reflected over the power incident is just going to depend on the ratio of A reflected over A incident. Oh, and I need A incident in front of here, right? My equation has an A incident we multiply by. So this squared, all right? Now, remember, the power can depend on things other than the amplitude. Depends on the frequency, the wave velocity, who knows what else in the waterways. But all of that stuff should be the same on the reflected side because it's the same medium for incident and reflected waves. It's harder on the transmitted side, so that's why we're finding it on the reflected side. And that's just going to be the ratio of this to A incident is just, right, that just cancels out the A incident, and we're left with the square root of 1/2 minus 1 divided by the square root of 1/2 plus 1, square that, right? There's the ratio of our powers. And then the fraction of power transmitted is just going to be 1 minus this. And I'll leave the algebra and plugging things into the calculator to you, but that's the basic way to work a problem like this.